Hi everyone. Today I will be discussing my work on developing a long default classification model for the M4 practice handshake. This video will cover three key aspects: how I improved the performance of my classifier, and how I access and improved its fit, and what I would do to further enhance the model if given more time and resources. So let's dive in and explore each of these areas in more detail. So first one, we need to improve model performance. One of the most critical steps in improving model performance is effective feature engineering. Feature engineering is essential because it directly impacts how well the model can understand and interpret the underlying patterns in the data. I applied one-hot encoding to categorical variables like person home ownership and loan intent to ensure that they were appropriately utilized by machine learning, which typically require numerical input. This process is essential for models like ChatGPT, which can struggle with categorical data without proper processing. In addition to one-hot encoding, I also derived new features such as loan-to-income ratio, which helps determine whether an applicant is overextending financially. This is a critical factor when predicting loan defaults, as applications with a high loan-to-come ratio are more likely to default on their loans. By incorporating this feature, the model can better assess appliance financial stability. To further improve the model's performance, I applied feature scaling to numerical attributes such as person income and loan amount. Feature scaling is particularly important when using models like logistic regression or gradient boosting, which are sensitive to the scale of the input features. By standardizing or normalizing these features, I ensured that they were on the same scale, preventing any single feature from dominating the model's decision-making process. Moving on to model selection, I want to find the best performing model for this classification task. To do so, I experimented with three different classifiers to maximize the F1 score, which balances precision and recall. The three models I tested were Random Forest. This is a robust model that handles linearity well, but can sometimes overfit if the trees are not pruned properly. Despite this, it performed well and gave a solid baseline for comparison. The second one is gradient boosting. This model offers high accuracy and can handle complex patterns in the data, but it can also be computationally expensive, particularly when the dataset is large. The third one is ChargeBoost. This model is known for its efficiency and effectiveness, especially with structured data. It uses boosting to iteratively improve predictions, leading to higher accuracy. After extensive testing, ChargeBoost yielded the highest F1 score, thanks to its ability to optimize through boosting. However, I made sure to carefully tune the other models as well, ensuring a fair comparison before selecting ChargeBoost as the final model. Another challenge I faced during this project was class imbalance. In the dataset, long defaults are less frequent than non-defaults, making it difficult for the model to accurately predict the minority class. To address it, I used the synthetic minority oversampling technique, which generates synthetic examples for the minority class to balance the dataset. This helps model learn more effectively from the minority class without simply overfitting to the majority class. Additionally, I experimented with class weighting and threshold tuning. By adjusting the decision boundary, I was able to find a balance that improved recall without drastically reducing precision. This is crucial in long default prediction because we want to ensure that we correctly identify as many defaults as possible while minimizing false positives, where we incorrectly predict that a loan will default when it actually won't. To fine-tune the model further, I implemented parameter tuning using both grid search and random search. For ChatGPT, I focused on the parameters such as learning rates, max dips, and N estimators. By optimizing these hyperparameters, I was able to improve the model's performance significantly. After tuning, the F1 score improved by approximately percentage, which demonstrate the importance of hyperparameters optimization in enhanced model performance. So right now we need to access and improve model fit. Now let's talk about how I access and improve the fit of the model. Ensure that the model the model is stable and generalized well to unseen data is crucial in many machine learning projects. To prevent overfitting or underfitting, I used k-fold cross-validation instead of simple train test split. This technique helped to ensure the model's performance is consistent across different subsets of the data, providing a more generalized estimate of how it will be performed in production. To further assess whether the model was overfitting or underfitting, I plotted learning curves. A learning curve shows how the training error and validation error change as more data is fed into the model. If the training error is significantly lower than the validation error, it suggests overfitting, which I addressed by applying regularization techniques and pruning in decision tree. On the other hand, if both error was high, it indicated underfitting, promoting me to increase the model's complexity, either by adding more features or using a more powerful model. Another key tool in evaluating model fit is the confusion matrix. By analyzing the confusion matrix, I could assess the trade-off between false positive and false negatives. False positives, where the model incorrectly approved a risky loan, could lead to significant financial losses. On the other hand, false negatives, or the model reject a good appliance, could hurt the business by missing out on potential revenue. Analyzing these trade-offs allow me to adjust the decision threshold to better align the model's performance with business priority. I also examined the precision recall curve, which is especially useful for imbalanced datasets. This curve helps in understanding the model's performance at different thresholds, and I adjust the decision threshold accordingly to strike the right balance between recall and precision based on the business needs. If given more time and resources, I would look into external data integration to further enhance the prediction accuracy of the model. Incorporating the macroeconomic indicators like interest rate, inflation, and unemployment rates could provide valuable insight into loan default trends and help improve the model's predictive power. Additionally, integrating credit bureau data could offer deeper insight into applicants' financial histories beyond just the provided credit score. This would provide a more comprehensive view of applicants' creditworthiness and could improve the model's ability to predict defaults accurately. Once the model is deployed, it is important to continuously monitor its performance to detect any potential issues, such as data drift, which occurs when the statistical properties of the input data change over time. To address it, I will implement a monitoring system to track changes in the distribution of input features. If any significant change are detected, the model can be retrained with updated data to maintain its accuracy. Additionally, periodic retraining with fresh data would help ensure the model continues to perform well as long market condition evolves. So generally, I improve model performance through combination of feature engineering, model selection, class balancing, and hyperparametric tuning. I access model fit using techniques like cross-validation, learning curves, and confusion metric analysis. Give more time, I would incorporate external data to improve prediction accuracy and implement a robust monitoring system to track more model performance in production. And that's all I can provide to you guys. Thanks for watching. Thanks for watching.